Hi everyone, welcome to the tutorial video of QUIC. I made this tutorial around the question given in the task sheet, which first is structure the tutorial so well and almost cover every topic to understand QUIC. Let's first get a quick overview of what we're going to discuss in this video. So we're going to discuss about QUIC, of course, how it is more efficient, fast, functionality and framework of QUIC, security related issues with QUIC and lot more. So it was Google who developed this transport layer protocol, and basically it is designed to minimize the latency and enhance the performance and make things fast on internet because saving time is everything. Nobody likes latency, right? So the question guys is, what is QUIC? Basically QUIC stands for Quick UDP Internet Connection. As I told it before, it is developed by Google. So what it actually do, like what is the main goal of QUIC? Basically it aims to reduce the latency in the internet connection compared to the TCP. It achieved this by implementing on top of the UDP. As you can see here, the QUIC is implemented on top of the UDP rather than TCP, which allows for greater flexibility and faster deployment. QUIC integrates features such as the congestion control, multiplexing, forward error correction, and connection migration. We're gonna discuss about these features in more details further in this video. So all you have to know is that QUIC streamlines communication by combining transport and security into the single protocol. On a single connection, many streams of data may move simultaneously, removing head-of-line blocking and cutting down on latency. Why do we need QUIC? Before QUIC, the world of internet was using TCP/UDP as a transport layer protocol, where TCP is reliable but slow and UDP is fast but lack of reliability, as we all know. So here, QUIC addresses several limitations present in this traditional protocol. Like it first reduces the latency, and it do so by minimizing the number of the round trip required for connection establishment and data transmission. As you can see in this figure, the TT of TCP is more than QUIC because TCP handshake is a three-way handshake which requires more time. As you can see here, it requires about 100 milliseconds of time compared to the QUIC, which actually requires 0 milliseconds of time. Second thing is that it improves the congestion control, as it is featured pluggable congestion control algorithm and provide richer information to these algorithms compared to the TCP. This allows for a more efficient bandwidth utilization and better adaptation to network conditions, ultimately leading to the smoother data transmission. Third thing is multiplexing. Multiplexing basically means that sending multiple data. Since all packet in TCP actually transferred through the single pipeline, which sometimes leads to the head-of-line blocking. When the packet gets delayed or lost, then it creates the situation of head-of-line blocking. But in QUIC, there are the multiple pipelines. As you can see in this image, there are the multiple pipelines known as tree, and this solves the problem of head-of-line blocking, as unlike TCP, packet loss or delay on one stream does not affect the progress of the other stream in the QUIC, as they are traveling through the multiple data streams. The fourth point is the forward error correction. We will talk about it in the next slide in more detail. And the fifth point is the connection migration. Another reason why we need QUIC is because of this feature of QUIC. QUIC connection are identified by a connection ID rather than the IP address and port number. This allows for seamless migration for connection between different network interface or IP addresses, such as switching from Wi-Fi to cellular network without interpreting ongoing data transmission. Let's move to the next slide. Functionalities of QUIC. Till now, actually, we actually discussed a lot of its functionality. Let me just recall you one more time about its basic functionality. The first thing is the connection establishment. Basically, QUIC allows for fast and secure establishment of connection between endpoints, often requires fewer round trip compared to the TCP. The next feature is the multiplexing. QUIC supports the multiplexing of multiple streams within a single connection, allowing for a concurrent transmission of data without head-of-line blocking issue, which we have discussed. And another important feature is the forward error correction. So first, let me tell you what is FEC, forward error correction. It is the technique used in communication system to enhance reliability and by adding redundant information to the transmission data. This redundancy allows the receiver to correct error without requiring retransmission from the sender. In the QUIC protocol, FEC employed to recover from packet loss without waiting for the retransmission. Let me tell you how it works. When a sender transmits data packet, it also sends additional FEC packet containing redundant information. The receiver uses both the original packet and the FEC packet to reconstruct the lost and corrupted data. If packet is lost during the transmission, the receiver can use the FEC information to recover the missing data. This approach reduces the need of retransmission, which can be especially beneficial for real-time application like streaming media. And the fifth functionality of QUIC is the connection migration. As discussed, this facilitates seamless migration of connection between different network interface or IP addresses without interpretation. Let's move to the next slide, which is frame format of QUIC. So as you can see in this image, let's break down image into the parts. Here are the parts of the QUIC packet labeled in this image. So first is the QUIC header. The QUIC header, it is typically resides at the beginning of the packet. As you can see, it contains the flag which controls behavior of packet, connection ID. This is a unique identifier for connection. The next thing is the packet number. It is another unique identifier for packet within the connection. It basically contains the essential information for processing the packet, include the packet type, payload length, and other flags. Then we have the stream frame header. So this contains information about the stream frames such as the stream ID and the offset of the data within the stream. Then we have the stream frame payload. This contains the actual data that is being transported. Then we have the acknowledged frame. This frame is used to acknowledge receipts of packets. Next we have the QUIC payload. It sits after the header section, as you can see in this image, containing information about the packet itself. This payload can hold various type of data depending on the application using QUIC. And at the last, we can say QUIC MAC. So the QUIC packet, there's the QUIC packet, is protected by a MAC. MAC is actually the message authentication code. So it is a cryptographic code added to the packet that allows the receiver to verify if the data hasn't been altered during the transit. So this was all about the QUIC packet and the frame. Let's move to the next slide. So in this slide, we're going to discuss the advantages and disadvantages of QUIC. So basically, QUIC functionalities are its advantages only, reduce latency. As it's designed to reduce latency only compared to the protocol like TCP, it achieves this through features such as faster connection establishment, multiplexing, resulting in the quicker data transmission. Next advantage of QUIC we have is improved congestion control. So as we have discussed, QUIC provides richer information to congestion control algorithm compared to the TCP, allowing for more efficient bandwidth utilization and better adaptation to network conditions. The next advantage of using QUIC is multiplexing without head-of-line blocking. So unlike TCP, which suffers from head-of-line blocking issues, QUIC allows for multiplexed operation, where packet loss or delay on one stream does not affect the progress of other stream, leading to improved performances. The next advantage of using QUIC is forward error correction. We have discussed this in detail in our previous slide, and connection migration that we have discussed. So these all were the advantages of QUIC. So is QUIC all sunshine and rainbow? Actually no, it do have some of its disadvantages too. Let's talk about it. The first thing is the compatibility. Since QUIC is relatively new compared to the TCP, widespread adoption may take time. Compatibility issues may arise when communication with endpoints that do not support QUIC. The next advantage of using QUIC is increased complexity. No doubt, QUIC is more complex than TCP due to its cross-layer approach to transport and security. Implementing and debugging QUIC can be challenging for the developer. The another disadvantage of using QUIC is the resource consumption. QUIC introduces additional overhead compared to the UDP due to the features such as the encryption and connection management, which may impact the resource consumption on devices with limited processing power or bandwidth. Next is limited support. While major web browser and services are increasingly adopting QUIC, no doubt, supporting for the protocol may not be universal across all platform and applications, leading to the fragmentation in the networking ecosystem. So, network application using QUIC. The first network application which uses QUIC is the web browsing and HTTP3. So HTTP3, the latest version of the hypertext transfer protocol, is built on top of QUIC. As the QUIC enhances web browsing by reducing latency and improving data transfer speed. The next is the Google application. as it is developed by Google. So almost all Google application uses the QUIC to prioritize faster loading time, smoother video streaming, and improved responsiveness, which enhances the user experience. The next application which uses QUIC is video streaming and content delivery. So we all use this YouTube, right? It's one of the most popular video streaming platform, and it uses QUIC extensively. By reducing round trip time and improving reliability, QUIC ensures smoother video playback and faster content delivery. So it all results that one can enjoy a video of his favorite creator without any latency, provided internet connection is good enough. Next application which uses QUIC is online multiplayer gaming. So we all play or see many online games which require low latency for smoother experience. Like who want to play the game which lags so much, right? So many online gaming uses QUIC, which reduce lag and faster the data exchange, which definitely benefits multiplayer games. Let's now talk about the security threats related to the QUIC. So there is a quote, better don't be too quick. The first security threat is firewall bypass. As a QUIC operator over operates over UDP, which is often less restricted than TCP in many network environments. It can bypass traditional firewall rules that focus on TCP traffic. This allows a client to access services that might otherwise be blocked, creating potential security loophole. The next thing is stateless firewall limitation. So traditional stateful firewall rely on tracking TCP connection to enforce security policies. However, QUIC stateless nature make it challenging for these firewalls to efficiently monitor and control traffic. The next security threat we have is limited protocol visibility. So QUIC encrypts most of its protocol information, make it difficult for network security tools such as the intrusion detection system, that is IDS, and intrusion prevention system IPS, to inspect and detect malicious activity effectively. This can leave network vulnerable to various threats, including command and control traffic. The next we have is the potential protocol-based attack. So while QUIC prioritizes security and privacy, there is always a possibility of utilizing the protocol itself to execute attacks. So this was all about the security threats related to the QUIC. So we should consider this before using QUIC. Next, let's now discuss how does QUIC achieve zero RTT connection. So as we know that TCP uses the three-way handshake to establish connection. The connection is full duplex, and both sides synchronize and acknowledge each other. The exchange of these 4 flags is performed in 3 steps, as you can see in this image. First is synchronization, then synchronization plus acknowledgement, and then acknowledgement from the client side. And then one can request and send the data to the server. So this process takes around 100 milliseconds of time, and when we add the TLS to it, which is a security layer, it will then take about the 200 milliseconds of time. So as we are particularly interested in the QUIC, so let's understand its handshake. So during the very first time when the QUIC is making connection to the server, so at the initial stage it takes 1 RTT, but once the connection is established, then for every request no more handshake or connection establishment is required. So at the initial stage, first the the client hello will be sent, and then the server hello will be sent, and then one can request data or send data to the server. So the client can simple request and get data on the basis of the initial connection establishment. As you can see, now after the initial setup, QUIC achieves the zero RTT connection. So the question is, how does QUIC achieve the zero RTT connection? It does so through the combination of clever design choices and cryptographic techniques. Let's explore how it accomplishes this. So the first thing is the connection disruption. QUIC allows for session disruption by reusing previously established cryptographic keys. The next is the zero RTT handshake. After the initial connection, QUIC enables the client to send data in the very first packet without waiting for the server response. The client includes the encrypted payload in the zero RTT packet. We discussed the QUIC packet in the previous slides. So the server decrypts the payload using the session ticket and processes the request. So let's now look quick in the Wireshark. Let's analyze quick in the Wireshark. So I just opened YouTube in my Firefox. So the first packet is sent from the client to the server. As you can see here, this packet is for establishing the connection. Uh, Here we can see the more details about this packet. The packet length is this 619, and it is a long header. Long header is basically used to exchange the initial data. And here we can see the version. This version indicates the version of draft we are using. Then we can see the connection ID, destination connection ID length, which is 13, and the connection ID is encrypted. The source connection ID length is 3, and source connection ID is also encrypted here. And the packet number is 0. So packet number, connection ID, these are the fields that I discussed in the quick packet slide. So the packet number is 0. Remember this, we're gonna use this packet number in my further explanation. You can see UDP. The QUIC is built on the UDP, so it is possible to have two QUIC packets in one UDP. This is the client hello. Now the destination responds with the server hello. As you can see, the destination responds with the server hello, and it also uses the long header to exchange the data. And here you can see the destination connection ID and the source connection ID remains the same. So the packet number is 0, and initially the client sends the packet 0, and it acknowledges that packet. Largest acknowledges 0, that it acknowledges, okay, you sent me the packet 0, I acknowledged it. Check the payload. We used the short header. Now here we cannot see the version because QUIC sent the version at the initial connection establishment, so it is no more needed here. Client hello done, server hello done, and then client is destination can exchange their packets. So this was all about the QUIC. Thanks for watching.